Okay, when we look at this picture, these are the kind of things that you'll see to identify. Each of these clear spots, each of these spots is supposed to represent a different kind of atom. So in all these examples, there's two kinds of atoms. There's the clear ones and the dark ones. It says, the first question says, which one represents a pure element? On page 12, when we classified elements, we said that all the atoms were the same, and they're not joined together. So picture 4, all the atoms are the same, and they are not joined together. So this would be a pure element. A mixture of two elements, the atoms would not be bonded together still, and it has to be picture number 2. Okay, you got the clear atoms, whatever element that is, and the dark ones. Number 3 says, which picture represents a pure compound? A compound is 2 or more elements bonded together in a ratio. But they should all be the same if it's pure. You look over here at 5. It has dark, clear, dark, and clear, dark, clear. They're not the same, so it's not pure. This one shows a single clear and a clear bonded to a dark. They're not the same, so it's not pure. Over here, they're all the same. They're all clear, dark, clear. So that has to be number 1. It says, which picture represents a mixture of two compounds? Number 5 shows the compound clear, dark, clear, and dark, clear, dark. The last question says, which picture represents a mixture of a compound and an element? Here we have the single atom, this clear, that element, and then we have this compound with a clear and a dark. So it's number 3. Okay. And then you should look over your notes for a review at the bottom of this page. Properties of matter is something else that is emphasized on the benchmark. So I want to take a quick review of page 13. There are 2 big kinds of properties. There are physical properties and there are chemical properties. A physical property is a characteristic that we can observe or measure without changing the identity of the substance. When we say we can observe it, that means we can detect it with our 5 senses. So it's something we might smell, something we see about it, something we hear about it, something that the way it might taste, how it feels, if it's hot or if it's cold, if it's rough or if it's smooth. Okay, so things that we can see, like the color, the shape, the size, the smell. We can measure the temperature it melts at. We can observe whether or not it's magnetic. Obviously, these are not the only physical properties. Pretty much if a word is an adjective, that word describes a physical property. So if you're tall, if you're short, it can be used to separate a mixture. One of the key things about mixtures is that they can be separated by physical means. So we looked at a video early where the kids used a magnet to separate iron from sand. A physical property is its mass. If you put it on a balance beam, you can measure the mass of an object. Another physical property is the space that it takes up. The density is something else we can measure. If we know the mass and we know the volume, we can calculate the density. Solubility, how much of it might dissolve at a given temperature. So if we have a glass of water at room temperature, we can observe or measure how much sugar will dissolve in that water at room temperature before it starts to settle to the bottom. We can also measure whether it conducts heat and electricity. None of these things change the identity of the property. When you observe that the wires in the wall conduct heat or electricity, they stay wires. They don't change their identity. Now, we have physical properties and we have chemical properties. We also have physical changes and chemical changes. Changes are something that happens. It's an actual action. Okay? Properties describe things. So the things up here, it describes the color, it describes the shape, it describes the size, it describes whether or not it's magnetic. A change is when it actually happens. So if we change the shape by crumpling up a piece of paper, crumpling is a physical change, and it has an ing on the end because it's happening. Okay? It's changing a substance, size, shape, state, or matter, and it does not change the identity. Okay? So it could be a change in any of these things. We tear it, we cut it, we melt it. Okay? All of those things, you notice they all have ing on the end. It's actually happening because it's a change. It's what we're doing to change it, but we're not making new substances when we do it. Like if you tear a piece of paper, it's still, you got two pieces, but it's still paper. If you cut your hair, you got hair that's still attached to your head, and you got hair on the floor, but it's still hair. If you melt an ice cube, okay, the melting is a change, but it was, the ice was H2O when it was frozen, and in the liquid puddle, it's still H2O. Chemical properties indicate how a substance will change or react to make a new substance. Okay? We can't just observe these, we have to test for them to see if it will happen. For example, you can't tell if it'll burn by looking at it. Okay, now there's a lot of things you probably think, well, I know, like looking at wood, that it will burn. That's because it's been tested before and you've seen it happen. You know what'll burn because you've seen it happen. Flammability, combustibility, acidity, reactivity. Okay. Chemical changes, again, are when it's actually happening. Okay. It creates a new substance. So if I say iron will rust, that is a chemical property. The new substance is the rust. I'm just describing the iron. It's not rusting right now. I just say iron can rust. If I say the iron is rusting, that's an actual chemical change because it's happening. Okay. Chemical changes are sometimes indicated by a change in temperature, smell, the formation of a gas or bubbles. Okay. And we saw how Bill Nye used chemical changes to separate water into hydrogen and oxygen. Examples, when you burn wood or digesting or cooking, all those things are chemical changes. Okay, the Earth's surface, in last year's science, when it weathers, it involves both physical and chemical changes. Physical would be like when rocks bust apart. If they get water in a crack during the winter and the water freezes, it expands and it'll split the rock. It would be chemical if the rain is acidic and it causes the rocks to deteriorate and undergo chemical changes. Okay? We can use both physical and chemical properties to identify unknown substances. So for example, something is solid, shiny, yellow, dense. It doesn't burn, that's a chemical property, and it's a metal. Okay, what is it? It's gold. Okay? And the last thing to review on this page is the law of conservation of mass. Okay? So it says the masses of all the substances present before a chemical change equal the mass of the substances after. Mass is not lost or gained, created or destroyed. So what that's saying is when you burn the wood, the atoms don't disappear. They're in the ashes, they're in the smoke. If we could catch all of them, find the mass of all the smoke and all the mass of all the ashes, and there was probably water in the wood because you heard the steam go out of it. We catch all the steam and everything. When we find the mass afterwards, it would equal the mass before. That's because during those changes, the atoms don't just disappear. This is page 16 in your notes. Another important thing that we reviewed a couple of times this first 9 weeks are Dalton's characteristics of atoms. Dalton said that atoms could not be broken into smaller pieces. He believed that they were like tiny hard marbles or rigid spheres that were impossible to break. This is not what we think today. Today, from Rutherford on, we know that the atom is mostly empty space. Some of the things that Dalton said should seem obvious today. For example, he said in any element, all the atoms are exactly alike. We talked about this in classification of matter. In a sample of gold, all the gold atoms are the same. That's why it's pure, and it's not a mixture. This idea explains why an element always has the same properties. So no matter where we find gold, gold is gold. Well, and he also said like all oxygen atoms are like every other oxygen atom. Well, since oxygen and gold are different, okay, Dalton also realized that atoms of different elements were different. This is why it explains why different elements have their own unique set of properties. This is why the properties of gold are different than the properties of oxygen. Okay. Dalton also realized that atoms of two or more elements could combine to form a compound. A compound cannot be broken down, can be broken down into elements.
Number 2, teachers, please release your students.
So Dalton concluded that compounds had to be made of atoms as well. So for example, hydrogen can bond to oxygen. It makes water when there's 2 hydrogen and an oxygen. And we saw in one of the videos, you could break the oxygen apart from the hydrogen and get back separate hydrogen gas and oxygen gas. As we're studying on the periodic table now, atoms of each element have a unique mass. When Dalton did this in the 1800s, he was not actually able to measure the mass of individual atoms. So he found the mass of a group of atoms. The masses of an elements in a compound are always in a constant ratio. That ratio is the formula. Water is a compound. It's made up of 2 hydrogens, 1 oxygen. Any pure sample of water, the ratio of the mass of hydrogen and oxygen is always the same. Okay, so over here I showed you the formula. It's H2O. The mass of hydrogen is 1. The mass of oxygen is 16. So if we take the 2 hydrogens, their mass each, 1 plus 1 is 2. The mass of the oxygen is 16, so the ratio of the masses is always 2 to 16 because there's a formula. It's always 2 hydrogens to 1 oxygen. The force that holds atoms together is called a chemical bond. They're chemicals, and they're bonded together, so it's a chemical bond.
Number 3, teachers, please release your students. Number 3, teachers, please release your students.
When 2 or more atoms are joined together, the new substance is called a compound or a molecule. There's a little picture where we labeled the different parts. A chemical bond is what's holding this hydrogen to the oxygen. This chemical is bonded to this chemical, and it's called a chemical bond. On the benchmark is the kinetic theory. Page 17 in your notes. Kinetic theory explains how the particles in matter behave. There's 3 parts of the kinetic theory. The first part we already know. Everything's made up of tiny particles. Particles are constantly moving around. They bump into each other. Okay, so one of the important things about this motion is as you heat them, they speed up. As you cool them, they slow down. Thermal energy is the total energy of the potential and kinetic energy of a material's particles. As it's the total energy It depends on how many particles there are. Temperature is the average, how fast the particles are moving. Temperature does not depend on how many particles there are. The lower the temperature, the slower the particles move. When we raise the temperature, the faster the particles move. Page 20 of your notes summarizes some of the things that we learned in the kinetic theory. The total energy of a material of particles is thermal. The average is called temperature. The four common states of matter are solid, liquid, gas, and plasma, which is not very common on Earth. But since the sun is made out of plasma, it's the most common in the universe. Out of the three states of matter, a gas has the most kinetic energy as the particles are moving around the fastest. The heat of vaporization is the energy necessary to turn a liquid into a gas. Okay. Does a solid have a definite shape? You betcha. Does it have a definite volume? Yes. Liquids? No. When you pour a liquid into a container, it takes the shape of its container. They do have a definite volume. It doesn't matter if you pour them into a dish or into a glass, the amount of liquid stays the same. Gases do not have a definite shape, and they do not have a definite volume. We learned about two different kinds of solids, amorphous and crystalline. Amorphous solids did not have a definite melting point. The particles were not in a repeating pattern. Crystalline solids like ice had a definite melting point. It melts at 0 degrees Celsius. It's also the temperature it freezes at. And the particles are arranged in a repeating pattern. That pattern is called crystals. On page 23 of your notes is the phase change graph. This was exactly like the phase change quiz. Okay. So we see as this solid is heated, okay, we have this really cold solid, this piece of ice. It started off maybe in a deep freeze, it was -20. It raises up until the temperature goes solid. After this time where it's melting, it's a liquid. So we have really cold water, and it heats up, and then it goes through phase change, and it becomes a gas. It's time when the temperature is staying the same is when it's melting, or freezing when the particles are fusing back together. Up here is vaporization or boiling. If we're cooling it, it's when it's condensing and going from a gas back to a liquid. The heat necessary to turn the solid into a liquid and unfuse the particles is called the heat of fusion. The heat necessary to break the particles apart from a liquid and turn them into a gas is called the heat of vaporization. It's the heat necessary to vaporize the liquid. During the times when it's changing phase, the temperature does not change. So if we look at here at the beginning of when it started to melt, temperature is 0. In the middle, it's still 0. At the end, it's still going to be 0. The same thing is happening during the time when it's vaporizing. At the beginning of line D, it's 100. In the middle of line D, it's still 100. At the end of line D, it's still 100. You see this at home. When you boil water on the stove, it stays at a constant temperature. The water doesn't keep getting hotter and hotter. When snow melts, if you stick a thermometer in it, it's always at 0 degrees. This is the boiling point, is 100. The melting point is 0. What's happening to the temperature along line A? Temperature along line A starts at -20. Line A ends where the temperature is 0, so it goes up 20 degrees. What happens to the heat along line A? Line A starts here at 0. Line A ends here at about 2, so it goes from 0 to 2. That's an increase. The material along line A is a solid. Along line B, the temperature remains the same. What happens to the heat? The heat increases from about 2 to 4. The name of that heat is the heat of fusion. Nature of the material along line B, we have a liquid and a solid. Think about when an ice cube melts. There's a puddle of water around the cube, and there's still the cube. So you have a solid and you have the liquid. Okay. Line C, the temperature is increasing. Line C starts at 0, ends at 100. That's an increase. The heat of line C starts here at 4. Line C ends here at about 9. So the heat increases. The nature of the material along line C is a liquid. Line D, during a phase change, the temperature remains the same. Line D starts here at 100. Line D ends here at 100. The heat, okay, we look down to the x-axis. Line D starts at about 9. Line D ends at 13. So the heat is increasing. The name of that heat to vaporize it is called the heat of vaporization. What is the nature of the material? Think about when you have a pan of water on the stove. There's water on the stove and there's gas above it, steam. So you have a liquid and a gas.